All right. So here's a bit more challenging equation to differentiate. Remember that if you have some function here and then you differentiate, there's a chain rule which says this doesn't do anything, but then that function has to be differentiated down there. That's like the one variable example of the chain rule, right? So we're going to apply that because gradient requires derivative with respect to x and then y. Let's calculate fx, which means that this thing doesn't change at all, but the derivative of this has to be put here. Now, what's the derivative of x cubed? That's 3x squared, but that's going to cancel with the 1/3 there. So you're going to get negative x squared. X differentiates to 1, that's what you get. On the other hand, f differentiated by y would be e to negative 1/3 x cubed plus x minus y squared. No change there, but then you have to pull this down here and differentiate. But all of the x's are going to differentiate to 0 because we're doing a partial with respect to y, right? You're considering x as constant, so the only thing that you get when you differentiate is the derivative of negative y squared, which is negative 2y. Okay, so now let's see what it means for the gradient of f to be 0. To get the critical point, you need e to negative 1/3 x cubed plus x minus y squared, negative x squared plus 1 to be 0. For this to be 0, you either need e to the negative 1/3 x cubed plus x minus y squared equals to 0, or negative x squared plus 1 equals to 0. See, anytime you have something multiplied to something equal to 0, that means either one of them should be 0, right? But can exponential functions be 0? The value of the exponential function is always positive, right? Whether you do e to the 0th power, which is 1, that's positive. E to the negative 2, that's 1 over e squared, which is also positive. It's always positive. No matter what number you plug into the exponential function, it's always positive. So this never happens. On the other hand, this one gives you negative x squared plus 1. Well, you can add x squared both sides, and you can say 1 is equal to x squared. And you can take the square root of it, so you get x equals to plus or minus 1. Don't forget to put the plus minus, okay? Both negative 1 and positive 1 are a solution to this. Okay, what about this one? In the same manner, this can't be 0, so the only way that the partial with respect to y is 0 is when you have negative 2y equals to 0. So you get y equals to 0. That gives us two critical points. The critical points are 1 comma 0 and negative 1 comma 0. For both of these, now we have to figure out what their Hessians are. Let's compute Hessians. To get the Hessians, you need fxx, which means now I have to take this one and differentiate by x. Now, however, there's a slight problem. Now, two functions of x are multiplied together, so when you differentiate this by x, you better be using the product rule, or else it's not correct. Okay, so we're going to differentiate this by using the product rule. Differentiate this, and don't do anything to this one, plus don't do anything to the first factor, but differentiate the second factor. And because the derivative of this is exactly this one, you just have this squared. And for this one, you differentiate by x, you get negative 2x. Okay. And then if you simplify further by, see, these two are the same, so you can factor that out. And this one, if you expand, that's x squared, x to the fourth minus 2x squared plus 1, and then there's a minus 2x. Okay, so that's fxx. Yes?
For the fxx for the first part, how did negative x squared plus 1 get squared?
Oh, because this one creates negative x squared plus 1, right? If you differentiate this by x, it creates this one. And then, so this with prime is this much, right? And then there's another negative x squared plus 1, so you have two of them. You see it?
Yeah.
Okay. All right, and then you have fxy. Okay, this time it's a lot easier because this time x is considered as a constant when you differentiate by y, so negative x squared plus 1 is merely a constant multiple. And if you have a constant multiple, then you're only differentiating this part. And if you differentiate this by y, you already have that here. So fxy is going to be negative e to the negative 1/3 x cubed plus x minus y squared times negative 2y times negative x squared plus 1. And because this is a challenging calculation, let's just skip the part where we verify by calculating also the fyx. They will be the same. Okay, now let's do fyy. Again, another product rule there. So you have to do prime negative 2y plus negative 2y prime. And that's going to give you, okay, so for the lack of time, let me skip some steps. This is going to be squared for the same reason this part became squared. So that's going to be 4y squared, and that's going to be negative 2. So you get 4y squared minus 2. If you do the calculation and simplify, that's what you get. Okay. All right, so what does that mean? That means the Hessian of f is going to be, well, the determinant of, and since it's a lot to write, let me just pull the e to the negative 1/3 x cubed plus x minus y squared so that it's written just once for all, okay? And then the remaining parts are x fourth minus 2x squared minus 2x plus 1 for fxx. And then this one, if I multiply it out, I'll just write it. So negative 2y minus x squared plus 1, negative 2y minus x squared plus 1, and then this is going to be 4y squared minus. Okay, so now we can calculate one by one. All right, so what do you get if you do hf 1 comma 0? That means I'm plugging in 0 into y and 1 into x. So if I plug in 1, well, it's some positive value. Let's see. If I plug 1, 2/3, yeah. So I get e to 2/3, okay? And then you get 1 plugged in, so you get negative 1, negative 4, negative 2 on the x-axis, okay? This will be 0 because y is 0 and 0 times anything is 0. And then if you plug in 0, you get negative 2. Okay? And then what happens here is that, well, if you multiply this inside and do AD minus BC, you get e to the 4/3 times 4, which is positive. Okay? So what does that means? For the case 1 comma 0, you get h of f to be positive. So it's definitely not a saddle. If it's not a saddle, then we look at the fxx, which is negative 2 e to the 2/3, which is negative. So that means at 1, 0, fxy has a what? Relative maximum, yes. Case 2, if you do negative 1, 0, then h of f at negative 1, 0, again, plugging in y equals to 0 will make these the same, but if you plug in negative 1 here, you get 1 minus 2 plus 2 minus 1. So it's going to be, you end up with, let's see, 1 minus 2 plus 2. Minus 2 and plus 2 is going to cancel, and you get 2. Okay. Therefore, when you do AD minus BC, you get a negative number. Okay. Technically, you have to multiply this into each one of them before you take the determinant, okay? But if you multiply it by a positive number, the determinant doesn't change the sign, okay? So it will, even after you multiply something, the sign doesn't change, so it's still negative. And then, furthermore, fxx, oh, but it's negative, but I don't even have to look for fxx. So what do we know? That means at negative 1, 0, fxy has a saddle point. That's it.